Next, we have the uncertainty principle. In the previous videos, we covered how a very small particle with energy and momentum is considered as a wave, in particular, a de Broglie wave or a matter wave. As a wave, it has a wavelength, and somewhere along or in this wavelength is the location of the particle. We also looked at the probability of finding the particle at a particular location or region in this wavelength. Zeroing in on the location of a particle in its wavelength turns out has some consequence. The uncertainty principle, Heisenberg's uncertainty principle, roughly states that if we know everything about where a particle is located, the uncertainty of the position of the particle is small, we know nothing about its momentum. That is to say, the uncertainty of momentum is large and vice versa. Delta x times delta p is greater than or equal to h bar over 2, where h bar is known as the reduced Planck's constant. It's equal to h divided by 2 pi. So delta x times delta p is equal to or greater than h bar over 2. If you make delta x small, you zero in on the location of the particle. To maintain the equality, to maintain the relationship, delta p will become large. The uncertainty of, or in the momentum, the uncertainty of momentum is large. The same and vice versa. If you zero in on if you focus on the momentum, the uncertainty in the location delta x will become large. If x is large, delta p is small. If delta p is large, delta x is small, and so on. The same relationship holds for energy and time, it turns out. Delta E times delta T is greater than or equal to h bar over 2. If delta E is large, delta T is small, and vice versa. The uncertainty principle. So that's it for now. In the next video, we'll continue our discussion on quantum mechanics. We'll take a look at Schrodinger's equation. So thank you for watching.